So today we'll be learning about the factor theorem, and we'll be learning how to apply it to factor higher order polynomials. So to start with, I want you guys to pause the video, and as a warm-up, I want you to do the division for each of these three. Okay, you can choose synthetic division or long division. Both will work. So if you did the division, you would see that in each case, we actually got a remainder of 0. So what that means is that all of these divisors actually divided equally into the dividend. And if something divides equally in, that means it's a factor. So in fact, all of these could have been written as the dividend equals the divisor times the quotient. Okay, and we wouldn't have had to put a remainder because the remainder was 0. And when you write it out in this method, you'll see that by doing the division, you've actually factored the polynomial. And same thing for the last one here. So because the remainder is 0 in each case, when we write it out like dividend equals divisor times quotient plus remainder, we end up with each of these polynomials just getting one step closer to factored form, or in some cases even in factored form. And we're going to see that that's very useful later on in the lesson when we actually start factoring higher order polynomials. So the factor theorem says x minus a is a factor of f at x if x minus a equals 0. So in other words, it says x minus a is a factor if the remainder is 0. Okay, so this is really just a special case of the remainder theorem when the remainder is 0. And it just tells us that whatever we divided by must have been a factor. Now, a little side note here, you'll notice that this statement has IFF. Okay, and that's not a spelling mistake. It stands for if and only if. And in math, what that means is it means that you can actually switch the two sides of the statement, and the statement still holds true. Okay, so in other words, we can read this as if x minus a is a factor, then f at a equals 0. And we can also say if f at a equals 0, then x minus a must be a factor. Okay, so it's just that you can switch those two sides of your statement and it will still hold true, which is not always the case. So here's an example. They're asking us to show that x minus 2 is a factor. So to show that it's a factor, all we have to do is we have to show that the remainder is 0. So remember, we can find the remainder by just plugging in 2. And if we do that, we get 8 minus 12 plus 10 minus 6, and that would give us 0. So therefore, x minus 2 is a factor by the factor theorem. Here's a similar example to what we had in the remainder theorem. They're telling us that x plus 3 is a factor. They want us to find the k value. So remember, if we plug -3 into this cubic, since we know it's a factor, it's going to have to equal 0 because the remainder is always 0 when you divide by a factor. Okay, so I'm going to plug a -3 in. And I'm going to set it equal to 0, and I'm going to figure out what k value would make that true. here we'd have negative 27 plus 9k plus 12 minus 3 equals 0. We would get 9k equals 18. K would equal 2. So if k was 2, then x plus 3 would be a factor. And if you want to check that out, you could plug a 2 in for k, and then you could actually do the division yourself, and you would see that it does divide in equally. Now, why is this important? The factor theorem is what we will be using to factor polynomials that have a degree that are 3 or greater. Okay, because right now we have a lot of rules for factoring quadratics. Okay, right? We have simple quadratics, complex quadratics. We can do the quadratic formula to get the roots to it. But as soon as we get to a degree 3 or degree 4 or degree 5, all we really have is factor by grouping if it happens to work. Okay, for degree 3, we now know how to do sum and difference of cubes if it happens to be that exact form. Okay. So, to factor using the factor theorem, first what we're going to do is we're going to find a test factor, which we will call a, so that f at a equals 0. In other words, we're going to find a number that we can sub in to make our equation 0. And by the factor theorem, that would mean that x minus a would be a factor, right? Because if a makes it 0, x minus a is a factor. Our next step is going to be take our function, divide out x minus a to determine the quotient. Okay? And then we'll write it as f at x equals x minus a times q of x. And if we need to keep factoring, we'll keep going. And this will make a lot more sense once we do some examples. So here we have a cubic. They're asking us to factor this expression. Okay, really factor it fully. The first thing you should do is see if it does group. If it groups, it's going to be a faster method than using the factor theorem in synthetic division. Okay, in this case, it does not group. So what I'm going to do is I'm going to let f at x equal x cubed plus 5x squared plus 2x minus 8. And we need to find f at something equals 0. So what you're really going to do is you're going to plug in values and find something that makes it 0. Now, there are a finite number of values that you need to plug in. And the way that you can find those values is if the leading coefficient is 1, then you only actually have to look at the end value. So there you have an 8. The possible numbers you could plug in are only the factors of 8. So remember, the factors of 8 are 1, 2, 4, and 8. And each of these could be plus or minus. So at most, you'll have to plug in up to 8 numbers. Okay, it would never actually get that far because some of them will be factors. So you're just going to start at 1. Try plugging in 1 in your calculator into this expression. See if you get 0. So off to the side, I can plug it in here. And we'll actually see if it works out. So 1 cubed plus 5 times 1 squared plus 2 times 1 minus 8. So that would be 1 plus 5, which is 6, plus 2, which is 8, minus 8. It does, in fact, equal 0. And because it equals 0, we know that x minus 1 is a factor. Okay, and that's by the factor theorem. Because there was a 1 here, x minus 1 is a factor. And now that we know this is a factor, we know that it will divide out nicely out of this cubic. So So step 2 is going to be to actually do the synthetic division. So we're going to divide our cubic here by the divisor that we just found. Okay, just quickly doing synthetic division, pull down the 1, multiply by 1, add, multiply by 1, add, multiply by 1, add. And we already know that the remainder is 0, so if you don't get a remainder of 0, you've done something wrong. And then we have a constant term, an x term, and an x squared term. So we can rewrite this as f at x, which is that cubic, equals quotient times the divisor. So our divisor times the quotient that we just found. Okay. And we don't need to do a plus or remainder because the remainder is 0. So what we've actually done there is we have factored it so that now there's one bracket factored out, and the other bracket is a quadratic. And remember, we already know how to factor quadratics. So two numbers that multiply to 8 and add to 6, 4 and 2. I can factor this quadratic into x plus 4 and x plus 2. So there is my fully factored cubic. And we're done. So let's review these steps quickly. So the first thing we had to do is we had to find a number that we could plug in to make the expression 0. Once we found that number, that allowed us with the factor theorem to say that x minus that number was a factor. We then divided out, because we know if it's a factor it's going to divide out nicely. And then we rewrote it as divisor times quotient, and we kept going with factoring. So if you go to the next video, you'll see a couple more examples of how we factor higher order polynomials.